Welcome everybody to Code on the Beach. Welcome to the session, The Business of Machine Learning, a Pragmatic Approach. I'm super excited to be here. My name is Michael Mann. I'll just introduce myself and then I have a story to tell. I'm a software engineer for a company called NLP Logics here in Jacksonville, Florida. We're a predictive modeling, artificial intelligence, machine learning, and data visualization company here in town. As far as I know, we're the only one. I don't know of any other machine learning companies in town. But I've worked there for about 4 years now, and before that, I had about 18 years experience in traditional software development, and transitioning from traditional software development into machine learning was a big transition for me. It was a big mind shift for me to move away from the way that you build software to the way that you build machine learning models. It's very, very different, and it's like being a child again. You know, you're learning new things all the time, every single day, and so that's why I'm so excited about this topic. So I want to tell you a little story about this morning that sort of changed the talk completely that I had prepared. So it might shift a little bit. So we'll see how this works. But I don't know about you, but I listen to a lot of podcasts. I'm plugged in all the time. So if I'm in my car and I'm driving, I'm listening to a podcast. Typically, it's a technical podcast. It's on software development. It's on programming languages. It's on distributed systems, whatever. So I'm always, keeping in touch with what's happening in the industry. It's a very fast-moving industry. I think you could probably agree with that. It's a fast-moving industry, right? And so when I'm out walking my dog, I'm usually plugged in. I've got earphones in my ears, and I'm listening to, guess what? Technical podcasts. I'm listening to software engineering topics. I'm learning about the new trends in web development. I'm learning about new applications of machine learning in different businesses. I'm always plugged in. When I'm washing the dishes, I'm wearing earphones. It irritates the hell out of my wife because she'll talk to me and I will not be hearing her because I'll be washing dishes and listening to technical podcasts, learning about programming languages or what have you. But this morning I didn't have my phone with me. And so I was walking my dog without being plugged in, and I started to think about this talk. And I started to think about what I really wanted to accomplish with this talk. For the first time, I wasn't plugged in, and I could actually think. And what came to me was kind of a bold idea, and I hope you'll bear with me in this bold idea. But I feel like in Jacksonville specifically, and probably nationally in the United States, machine learning seems to be a bit sparse in terms of its application in businesses, right? You hear about companies like Stitch Fix, or you hear about companies like Google, or you hear about companies like Uber, or you hear about companies like Airbnb that are worth billions of dollars, and sure, they hire PhDs out of colleges, right, to work in their machine learning organizations that they've built. But you don't see it in your normal businesses around town. How many people in this room are using machine learning where they work right now? Okay, so there are a few. So I applaud that. I'm surprised by that, actually. Are you doing it yourself? Do you have a discipline in your organization that is around machine learning? Or are you outsourcing that? Okay, that's awesome. Is it a small team or do you have a large team? It's just you. So what I'm saying here is that it seems to be a sparsity situation that we have in that space. So it's either people who are going to investigate it in their spare time and digging in because they really want to learn, or maybe someone is promoting it from up above. But what I see more often than not is that there are not very many companies that are really using machine learning, and I want to change that today. I want to change it. And when I was walking my dog this morning, the thing that I started to think about was how infuriated I am about how machine learning is being communicated broadly. And the way that I perceive it being communicated broadly as something that's unapproachable, something that only PhDs can accomplish out of college, right? So you think about the big companies that are applying it, like Google and Uber. What are they doing? They're grabbing all the PhDs from all of these colleges, right? That have PhDs in machine learning or bioinformatics or whatever, right? So it seems like it's an unapproachable topic, and I want to change that today. I want to change it. I want to eliminate all of the complexity that is perceived around machine learning, and I want to distill it down to something that is very simple, that you can take with you in your work and apply it. That's my goal. And how am I going to achieve this goal? Well, the way I'm going to achieve this goal is I'm going to take you through some examples. I'm going to take you through a lot of code, but I'm going to publish all of this code on GitHub within a week or so. You can pull it down, you can use it, you can experiment with it, you can change it, you can do whatever you want to with it. But what I want to do is I want to frame these problems in a way that you can relate it to what you deal with in your work environment. Because the way I view machine learning is it's just another tool. Just like we as developers use programming languages as a tool to solve problems, machine learning is no different. It's a tool used to solve problems. But we have to put it in context of what it's good at. And so that's what I'm going to try to communicate today. Are you with me? All right, let's see if we can go on this journey together. Hopefully I'm successful. All right, I already talked about myself. You don't need to see my big face. I already talked about the goals today, probably in great detail. Okay, so what are we going to cover? I talked a little bit about that already, but what I want to do is I want to frame some problems that we can solve using machine learning, and I want to draw a relationship of those specific problems to things that you would deal with in a normal workday. That's the goal here. So, this is a machine learning talk, so my laptop must be amazing, right? Because that's what we hear. We hear about how, your computer has to be a GPU-enabled machine. It has to have 16 cores and 1,000 gigs of RAM. No. This laptop has 8 gigs of RAM. It has 2 CPU cores. It is not a powerful machine. In fact, this machine has a backstory to it, and that we have a data analytics boot camp that we put on every year for high school kids at NLP Logics, and this $200 laptop was purchased for that program. So we have high school kids that are using these laptops to build machine learning models, to execute SQL queries, to do data visualization. So the point of the whole thing here is to demonstrate that you don't need a beefy machine to enter into the world of machine learning. Some other tools that are a part of this talk is Python 3.7, SQL Server Express, VS Code, Postman, and a data set from the NFL that's on the Kaggle website, freely available. And again, the point here is that all of this stuff is absolutely free. None of these tools cost you anything. Data set doesn't cost you anything. And what I want to do is I want to take the NFL data set, and I know it's a bit detached from what you're used to working with, but that's okay, it's a data set. You work with data sets every day, right? This is just another data set. So just think of it in the context of a data set. So here I talk about the beginning, but the beginning all changed this morning. But I'll go ahead and talk about this a little bit. I was talking with one of my coworkers, Ben Webster, who is a statistician, mathematician at Logix, and he's been with the company since almost the very beginning. He was the first employee hired there. Brilliant guy, getting his PhD in math. He tries to talk math to me. I try to absorb math from him. He's a terrible programmer, I'm a terrible mathematician, but we make a great team. But he was talking to me about a problem that he was solving for one of our customers. And the problem he was solving was around data analytics, effectively. So what we have is we have a customer who is presenting to their customers analytics about their own data, right? Statistical measures around their data, so that they can look at those statistical measures, and there are a lot of them, and then make business decisions based on those statistical measures. Beautiful UI, all great stuff. Okay, but the way that they were computing those statistical measures was compute intensive. Okay, because they had to be real-time statistical measures. Because what they did is they said, hey, you guys can put a date range in. Right? That's the death of any application, right? It's for someone to put a date range in. Because if they put a date range in, that means that they are driving the behavior of the data at that point, right? So, yes, they can put a date range in, and then they compute everything real time. And then they show it on the screen. Whether they use a programming language to crunch those numbers, or whether they use a back-end database and SQL to crunch those numbers, it really doesn't matter. The bottleneck is going to be on one end or the other. Okay, because they're doing it real time. So Ben and I got to talking about this, and he was thinking about how he could replace all of those statistical measures with a collection of machine learning models. And then I thought to myself, that is an interesting concept. Because you usually don't think of it that way. You usually don't think of machine learning that way, right? You compute an average, and you do it in SQL. You do an average over a value, right? But could you replace that with a machine learning model? Or you compute a standard deviation over a historical data set. Could you replace that with a machine learning model, right? And so now what you do is that you shift the burden of the computation off of the hardware completely, actually. Because a machine learning model is a self-contained data structure that can return a prediction based on inputs. There's no database, there's no application server, none of that. It doesn't exist, right? And so I'm thinking to myself, wow, that's an amazing idea from a couple of standpoints. One is performance is one, if you can pull it off. Cost is another, because I don't know about you guys, but if you're doing real-time calculations, somebody's paying for that CPU. Somebody's paying for that bandwidth. Somebody's paying for that programmer to develop all those computations, right? So there's a cost associated with it. And then I was also thinking about some of the problems that are being faced today in traditional software development, where complexity is so overwhelmed the space, where now everybody has to be a distributed systems expert. Everybody has to be a threading expert, right? Because we have to eke every bit of performance out of our hardware. But what if you could just eliminate some of that burden? Replace some of these computations with machine learning models? Well, you could sort of remove some of the strain off of your database server, remove some of the strain off of the programmer who's writing these silly computations, right? Instead of building business rules around your application. And that's another story we can talk about as well. So we had this conversation, I had my idea, and I'm like, wow, can we really do this? That was my thought. And if you're thinking it, then you know you can do it, right? You can do anything. Software developers can do anything. You can find a way, right? It's just putting constraints around the system that you're building and understanding what good is and what is not good, right? Having the ability to measure the success of what you're building and whether or not it fits within the constraints of the problem. So we're going to take a look at this NFL data set, and I just put some basic statistical measures up here which really aren't super meaningful, but one thing that kind of stands out to me is the number of rows that we're dealing with here. It's not quite 500,000 rows, not a huge data set, but we're doing this on a laptop that has 8 gigs of RAM. And I'm running every single application right now. I'm running SQL Server, Express. What else am I running on here? I'm running VS Code and a couple of other things. So I'm working in this constrained environment to demonstrate this to you. So what are we going to do with this data set? We're going to answer some questions in the data set. So have you ever had a database that you needed to get some answers out of? We all do, right? We do that all the time. We're trying to get answers out of our database. Whether we're doing it in code or we're doing it in SQL, right? We're going to use a machine learning model instead as a different tool. It's just a different tool. So as a tool in our tool chest, one of the things that I've used quite a bit is a random forest predictive model, which is a tree-based model. The random forest it's a fairly robust model. It works in both text classification problems, which I'll explain in just a moment, and it also works in regression problems. So it handles both numerical outputs and it handles string outputs. So it's robust from that standpoint. And it's also a fairly good predictor. It's pretty stable, I would say. Now, you're not going to do natural language processing with a regression, with a random forest, okay? But it's good for predicting numerical outputs and text outputs. Another thing about random forest, which is nice, is it has interpretability built in. And I don't know if you've listened to some of the media around deep learning, which is all the rage right now. Deep learning is not interpretable. They're considered to be black box models. You really don't understand how they arrived at the answer that they arrived at. And with things like GDPR, and I'm sure that the United States will have their own interpretability rules, that it's important to have interpretability in your models. How did it arrive at the answer that it arrived at, right? You can get some of that out of a random forest model. So that's why it's a very good first step into this space, in my opinion. And believe me, there are hundreds of models, different model types out there. But the one that I'm most familiar with is random forest. And so just like every other developer in the world, you go after the tools that you know, right? That work well. All right, so where are we going to start? We're going to start with model number 1. And here what we want to do is we want to take the NFL data set, which has 400,000 rows in it, and then we want to predict if a play is going to be a run or a pass play. Pretty simple thing, right? So you have different play types that will happen in a game. Hopefully, most of the plays are run or pass plays. I know you've got fumbles and you've got punts and you've got all this other stuff that we really don't care to predict at this time. But we want to stay in the space, a very simple space, and keep that space constrained, so we're going to look at runs and passes. So let's think about this for a minute, and think about it in the context of the data that you deal with every single day, right? And let's take the word predict out just for a moment. I don't want to get hung up on the word predict. But let's say we want to arrive at an answer to a question. We want to arrive at an answer to a question on a data set that we have. So can anyone give me, just think about your own data sets that you work with. Say that you're working with that data set, your boss has come to you, or you have had a problem that landed in your lap, and they said, hey, we want you to answer this question about your data set. And here are some rules that they need to conform to. How would you go about doing that? Anybody? No, so typically what I would do, like if I had a data set and I needed to get an answer, I need to understand the constraints of the system, right? So with all things, you have to understand the constraints of the system. So with the constraints of the system come rules, and that's what we do all the time, right? We write rules, right? In logic, you write rules, whether it's data transformation or whether it's if then else or whether it's, a combination of, pipe operators from this thing to that thing. You're basically building logic. You're building a bunch of rules. Okay, so one way to tackle a problem is to write a collection of rules to help you arrive at an answer, right? That's what we do all the time. Okay, so one way to do that would be just to code up a bunch of rules. But as a programmer, you have to codify your own understanding into those rules, right? So some of the things that you'll do is that you'll write some queries against the database. You'll take a look at the data. You'll start to see how the data is shaped. Like if we're looking at the run passes, maybe what we'll do is we'll sort of see visually, are there trends here? Let me write a couple of queries, see are there any patterns in this data that make sense, that sort of decide that this is more probable to be a pass and to be a run, right? We'll start to investigate the data to see if there are some patterns that we can see in the data. Has anybody ever done that before? Looked at the data to see if there are patterns in the data? Well, guess what? That's exactly what a machine learning model does. It looks at patterns in the data. That's what it does. And it does it way better than you or I can do. But there's a trick. You have to feed it. You have to feed it the right thing. But again, machine learning models do that. They basically develop internally. They build up the rules based on looking at the patterns in the data. So instead of writing rules, maybe what we can do is replace those rules with a machine learning model. But before we do that, I want to talk a little bit about what a training pipeline looks like. I want to completely demystify what a training pipeline is. Okay, so models have to be trained. They have to learn, right? Just like you, when you're looking at the data set, you're learning about the data set. You're looking for patterns in the data set. You're coming up with rules in your mind about the data set. Well, machine learning model does the same thing, right? But there is a way that it goes about it. And I want to kind of demystify what a training pipeline looks like for a machine learning model. It's not that complicated. It's actually really, really simple. So let's talk through it real quick. Okay, feature engineering. Feature engineering is nothing more than providing inputs to a model. That's all it is. It's nothing more, it's nothing less. It is a bit of an art and a bit of a science because what you're attempting to do here is to coax out the patterns that the model will pick up on to predict what you're trying to predict. So here we're trying to predict run and pass. What we need to do is we need to give the model something that it can look at and say, hey, there's a pattern here that I can see that's called a signal so that I know that this is a run or this is a pass. And that's what feature engineering is all about. At Logix, we work very, very closely with our mathematicians and statisticians because they know the math. And the math is what it's all about. And working with a mathematician and statistician is going to certainly help you along the way. That's why I'm blessed to work at Logix, because I work with mathematicians and statisticians all day long. Okay, so this language here, all it really means is turning a text string into a number. Machine learning models do not understand text. They do not understand text. I know you've heard about natural language processing. That's great. But at the end of the day, it's numbers. It's not text, it's numbers. So we have to take text and turn it into numbers if we have text features. So what could a text feature be? So A categorical variable would be something you can think of it as a category of things, a bucket of things, a list of things. So it could be fruit, for example, apple, peach, pear, whatever. It could be, it's a list of strings. But what we have to do is we have to take that list of strings, we have to turn it into numbers. Because that's what the machine learning models know. They know numbers, not strings. Let's see. Split data into test or train and cross-validation, also known as train and test. So the idea here is that it's just like being in school, right? You go to school, you're in class, hopefully you're paying attention, you're listening, your teacher is hopefully teaching you, you're absorbing it, and then at the end you get a test, right? So you learn the material, you absorb the material, and then when you take the test, hopefully the test is somewhat similar to the material that you learned in class and you do well. Machine learning model is the same way. So we have to train it, we have to show it examples, and then we test it to see how well it learned. It's the same exact thing. There's nothing different about it. And so what we do is we take our data set, our 400,000 rows, we take 70% of it, and we say, you're going to be our training set. And we take 30% of it, and we say, you're going to be our test set, or to validate how well you're learning. And believe me, we could do a whole session on how to split your data. All right, but we're not going to get into those details today. We're going to make it very, very simple because I want this to be a simple conversation. The last thing I want to do is to put up any barriers between you and this content. And then the last thing we do is we call predict. That's it. That's all there is. Now, I'm sure there's nuance where there are additional things, but really these are the main steps. And of course, we save our outputs. I mean, it's not super useful if you don't save your output. Machine learning model has a collection of outputs that I'm going to talk about what they are and what they're used for. But you need to save your output. You don't save your model to disk, you can't use it later. So it's kind of important that you save it. And then the other thing, I'll get into that, but you need to save your outputs. All right, so let's talk about what does the training process produce. All right, so, or at least this is what I produce. You can produce other things. You can produce an output that is not binary serialized. You can create an output that is JSON serialized or XML serialized or whatever the heck you want to do. But since I'm using Python and I'm using sklearn, we're going to binary serialize this puppy out to disk. Okay, a feature map. What is a feature map? So we talked about feature engineering earlier. So a feature map is exactly what it says it is. It is a map of the feature to an index position in a two-dimensional array. So let me take a step back and explain what that means. At the end of the day, when you call predict on your predictive model, you give it a two-dimensional array. That two-dimensional array holds a bunch of numbers. And then the predict call returns a prediction out. So what the feature map does is it tells you for the feature that you are giving to the model what index position that value belongs in the two-dimensional array. So if you have 10 features in your model and you have a feature called foo, and when you trained your model, that foo feature was in index position 9 in the array that you fed to the fit function that we'll talk about in a minute, then this feature map will say that that foo feature is in index position 5. And the reason why that's important is that when you call predict on your predictive model, that value needs to go in that exact position in your matrix. If it does not, then you'll get all kinds of crazy output. A factor map. So a factor map is similar to a feature map, but it is very specific to your string features in your model. So Again, the categorical features that we talked about earlier, so like the collection of fruits, if you have a collection of fruits in your model, which we wouldn't for the NFL data set, unless maybe they ate a banana that day or something, but the factor map basically says what is the name of the factor, so what is the name of the feature in the model. So again, we get back to foo again. And then what are the possible values of that? So the possible values of foo could be bar, baz, and bat. Okay, those are the string possible values for that. But they also have numerical values associated with them. Remember, because a machine learning model only knows numbers. So it will say that those three things map to numbers 1, 2, and 3. So that when we give bar to the model, that it knows to translate that to a 1. Or if we give baz to it, it knows to translate that to a 2. So those files are important, and these files are a creation of mine, by the way. This is not a standard, okay? But I find them to be extremely useful because what they do is they detach me from the technology. So I can write code in any language. Doesn't matter if it's Python, Java, C#, whatever, right? And I'm just parsing a text file. I'm not bound to Python. I'm not bound to the only other frameworks I know out there are like deep learning frameworks, but if there are other frameworks, I'm not bound to them specifically for loading up these artifacts. And so that's why I like this approach. But it's not a standard. So I'll just make that perfectly clear. Okay, list a feature importance ranking of the trained model. So feature importance basically says, what kind of influence did this feature have in the model? Which is sort of important, right? If you're creating features, you want to know, are they making an impact or not? Right? They may not be making any impact, or they may be detracting from other features in the model. So the feature importance will tell you that, or at least. And another thing that I like feature importance for is because you can look at your feature importance and you can say, oh, there's an opportunity to exploit something in the model by maybe combining two features together to create a new feature. So the feature importance map gives, or not a map, although you can create one from it, and I have. But the feature importance can help you in your feature engineering process. And so we'll take a look at that. Okay, and then another thing that we produce as an output is an output of all of our predictions as it relates to our test set or our cross-validation set. Why do we want this? Well, what we need to do is we need to analyze it, honestly. We need to look at it and see where our model is performing well, where it's not performing well, right? Now, there's a whole nother conversation about analyzing the performance of your model that we're not going to get into today. But this is an important output because it allows you to load it up in your tool of choice. It can be Excel, it can be Tableau, it can be any other data visualization tool that you want to use so that you can explore how your model is performing. And then maybe there are features that you engineered that are detracting from the accuracy of your model. And so analyzing the output is super important because when you're training a predictive model, the thing that you see is an aggregate measure. And that aggregate measure may be nice to look at. Like you can say, hey, I've got 87% accuracy, but that's an aggregate measure over a percentage of 400,000 rows. Okay? That doesn't mean that your model is great in all situations. It's an aggregate measure over a lot of data. And so it's useful to look at the performance of your model in the tool of your choice. Okay, so what I want to do now is I want to just pop over and take a look at these things quickly to put things in context. And hopefully this works because I can't see one screen and I can see another. And that looks looks terrible. Oh. I can't see. Oh. Can I kill that? Close. Yeah? Okay. And I might need to extend my displays here. But what I wanted to do is I just wanted to walk you through it real quick. Python. Okay, we are going to look at our train. Let's look at the train multiclass. So the train multiclass, what it does is it just trains the pass run model. Super simple. Has all those parts that I was talking about earlier. So if we scroll up to the top, okay, and if you're not familiar with Python, it really doesn't matter because all we're going to do is we're going to look at the building blocks that I talked about earlier. Okay, here's our split function at the very top. And so again, the split splits the data between test and train. And the thing just to notice here is this is super, super simple. And basically what it does is it takes in all of your data, and then what it does is it gets the indices from every row in that data. So every row in that data has an index associated with it, 0, 1, 2, 3, all the way through the end of 400,000. Okay? And then what we do is we take those indices and we shuffle them randomly. Yeah. Right here. Can you see that? All right, great. Yep. Sure, go ahead. Mm-hmm. Yep. Yeah. Same thing. Yep.
And are these models like available in some open source repo? For example, Java Spring has Native Central and JSON, for example.
Well, we're building the predictive models here. Yeah, these aren't pre-built models. We're just building them ourselves. Yep. So this is just a training pipeline of a predictive model. So, and this is all, I'm going to put all this stuff on GitHub, and you can pull it down, look at it, and do whatever you want to with it. But the thing that's interesting about all of these different, I built 3 different predictive models. The pipelines are exactly the same. Exactly the same. There's very little variation between any of the 3. The thing that varies is what is our accuracy metric and what is our model? And what are we measuring? Those are the 3 things that vary between the 3. And that's the message that I'm want to try to get across today. But here, what we do when we do this, we don't do anything special on the split. All we do is a 70-30 split. We randomly shuffle the indices and we kick them out. That's all we do. Super simple. Now, believe me, somebody could come in here and give an hour-long talk about how to do splits. All right, there's all kinds of art and science about how to do splits to get optimized. We're not talking about any of that stuff. All right, we're just talking about a straightforward split, 70-30, nothing special. Okay, we set a random seed so that the next time we run this, it will give us the same output every time given the same inputs. So if you run this thing, if you run this code once with the same data, a second time with the same data, the random seeds that you set here, even though this sounds a little weird, it'll give you the same output. You'll get exactly the same prediction, you'll get exactly the same model. That's the purpose of setting the random seeds. Here we just go grab the data. And then what I do here is I break things up into these buckets. So we have classification columns, which are the columns that are our string values. We have float calls, which are our numerical values. And what we have is we have meta calls, which are basically things that we're not specifically training the model on, but we want to use in some way, right? We may use them as a calculation to create a feature, right? So I break things up into those 3 spaces. Oh, poop. And then what we do is we specify what is our Y target. So our Y target is called play type. Play type is run pass. And there are other things in there too, like punt, fumble, whatever, but we're only focused on run and pass. So that's our play type. And then what we do is we create all the columns here, which are the combination of our float columns, our classification columns, and our meta columns, so that we go and grab only those columns out of our data set. I don't want to pull all the columns. I don't need all the columns. I just need the columns that I need to compute my features and train my model. Here, what we do is we isolate the data frame down to just run and pass records. I don't want to include fumbles, punts, anything like that, because that isn't what I'm trying to predict. Okay, so since I'm only wanting to predict run or pass, I don't need that. Other stuff is just noise. So we just eliminate it from our data set. And then here what I'm doing is I'm replacing any nans that are in the down variable because we have nulls in the data set. I'm just getting rid of those. Because if it's not a down, it's not a play. Right? It could be end of quarter, timeout, whatever. And again, analyzing your data set is probably the first step that you would want to take here just to sort of get familiar with it. I'm skipping over all of that. Here's where we compute all of our features. Nothing special. These are super simple functions. I don't really want to go into the calculation specifically. It's really too much detail. The thing here is that we have features that we compute over the data. One way to do this would be not to compute any features and just use the data in the raw, but you're going to have a really terrible model that way. And so the more that you can compute like numerical values and ratios and percentages and things like that, model will pick up on that signal. So here is just the space where I compute all of the features for the model. And again, none of this stuff is complicated. And then what I do is for the classification columns that I computed, so the features that I computed that were classification columns, I go ahead and combine the arrays. And now my classification columns variable has all of them. It has the things that I took from the data set, which I don't think were any, and then it takes all of the things that I computed as features. And then I do the same thing for the float calls. So I take the float calls that I pulled right out of the data set and I combine it with all the features that I computed. And then what I do is I split the data on the indices, and I get the indices back for both the train and the cross-validation. And so the convention that we use is X represents feature typically, and so we always use X to represent feature, and then underscore TR represents train, and underscore XV represents cross-val or test. It's just a naming convention that we use. Okay, and then here basically what I'm doing is I'm taking those indices and I'm creating these separate sets. Because I need these separate sets so that I can train on the training set, I can train on the cross-validation set, and then I can also have the metadata columns that I want to pump into my output file. Because it's kind of useful to have those additional columns if you want to look at that in the context of the performance of your model. Anybody work with Python normally? Okay, I'm not a Python expert. One thing I found is that if you don't do this reset index thing, what it'll do is it'll add an additional column to your data frame that is actually a number. That is not good. That's actually very bad. It's a sequential number, and if you do that, you're going to end up training with that as a feature in your model. Very bad stuff. So if you do the reset index and you do the drop true, it will not add that additional column to the data frame that is returned when you index it here. Python has this, it's not Python, it's pandas, so it's a data frame thing, and they use indexing as a way for you to have a row identity sort of a thing. And so if you don't do the drop true, it'll, like I said, it'll add a column to your data frame that has that in it. And since I'm using these to train the model on, that's not good. So that's why I do the drop true here. And what the reset index does is that since I have randomly shuffled indices, what I do here is I reset the index so that the train and the cross-validation set, the very first row starts with 1 and goes to n. And it's just better that way when you're writing the output file. And I'll show you why. Label encoders. The label encoders is one way that you can turn a string value into a numerical value. So we use a label encoder here. You don't have to use a label encoder. You can do your own thing if you want to. But for simplicity's sake, I just use a label encoder. And I use, since the label encoders are for every column that is a classification column, what I do is I create a dictionary that holds on to the relationship between that classification column and that specific label encoder. Because you can't train a label encoder on multiple things. It can only train on one thing. And so that's why I hold on to that relationship here. And then here we create the random forest classifier. Nothing special. And then we fit. So what fit does is it says, hey, I'm going to fit a line to this data, and now I'm going to create this data structure called a model. That's all there is to it. Now, random forest is a little more complicated because it goes in and it creates all of these trees, and then it has to average over trees, and that's an implementation detail. Don't worry about it. You don't have to understand the inner workings of the random forest algorithm. But when you fit, what it does is it creates a model, and that model lives in this RFC variable. And then what we do is we print our accuracy. And what we're doing here is since we're training a model over 2 labels, run and pass, to keep it fairly simple, what we do is we just use accuracy as a metric. And accuracy just says, did I get it right or did I not get it right? That's all it is. Very simple metric. And one of the things I wanted to do here is I wanted to show you how long this took to fit this model, actually to call predict on the model after you fit it. So after it's learned, how long do you think it takes to do a prediction over 400,000 rows? Anybody have an idea? How long? It's actually about a second. But think about it for a second here. If we had to write a SQL query to do this, or if we had to write logic to do this, how do you think it would perform? Do you think it would perform in a second? Hell no. No, absolutely not. It absolutely will not. And that's one of the messages that I want to try to get across is if you can leverage this as a tool in your tool chain, you can gain significant performance benefits out of it if the accuracy is within your tolerance. Okay, we're going down a little bit more. Okay, so we did predict. Now, what is predict proba? Predict proba is different from predict because here we're predicting a label, which is pass or run. But what predict proba does is it doesn't give me the label back of what it believes to be the right answer. But what it gives me back, since I have 2 classes, is it gives me a 2-dimensional array where an element in that array is an array of 2 values. Can anyone tell me what they think those 2 values are? That's right. It's the probability of each class. So if you have class 1, which is a pass, in the very first position, it'll give you the probability that it believes it's a pass. And the second position, it'll give you the probability that it believes that it is a run. So that's important, right? You want to know how confident it believes the answer is what it thinks it is. Because there's a big difference if you have a 50.01% probability that it's a pass, right? And it believes that it's a pass versus a 91% belief in that probability. So that probability is important in understanding how confident the model believes how correct it is. And so we want to capture that. Now, what you could do, and I didn't do it, but what you could do is that you could take the predict prob and not do the predict at all, and then you could sort of back into what the label is. I just did it as 2 steps because I wanted to keep it simple. Here's the feature importance. Looks complicated. It's not super complicated. This is actually code that I found online and pasted in here. So, but what this does is that this will give you a ranking of your feature importance from most to least. And here, what are we doing? Here I serialize the model. Okay, so we take the random forest classifier, we take the directory that we want to kick it to, we serialize it, which is just an implementation detail. We take a feature map, we save it, right? We take the training columns because that's what the features are, right? The features are the columns that we train the model on. So all we're doing is we're taking those training columns and then we're saying, hey, go kick them out to a file. And again, it's just a delimited text file. There's nothing special about it. And then if I have categorical features, what I do is I go ahead and save that out to my factor map. And I take the label encoder dictionary that I built up earlier, and I use that as a way to save out those factors to disk, because that's basically how I created them, right? Yep.
When it's outputting the importance of the features,
Mm-hmm.
Say for instance you combine two, like in this instance it would be like down and distance.
Mm-hmm.
Would it do that as a separate one?
So you would see, for every feature in your model, you'll see a score related to it. And so if you combine 2 features and you trained on that, you would see that in the feature importance list. And you would just see where it ranked among all of them. And then finally what we do is we have the output file that we generate. And this is really straightforward. We're just simply writing out a text file, a delimited text file, a comma-separated file. Nothing special. We kick out all of the rows that we trained the model on, all of the metadata rows that we defined up above. We go ahead and get our Y label, which is the thing that we are trying to predict. We get the Y hat, which is what did we actually predict. And then we get our confidence out of this cross-val Y hat probability, and then we just save it out. Nothing special. Super simple stuff. Yeah, and then we have these artifacts. So we talked about the feature map, we talked about the factor map, we talked about the model serialization, we talked about the file that we kick out so that we can do some analysis on our model to see, where is it doing well, where is it not doing well, so that we can sort of go back to the drawing board and do more feature engineering and improve upon our model. Does anybody have any questions so far about what I've covered? Yep.
So in this example, you're essentially predicting the next path, or you're just doing the next prediction from the previous 700 hours, or the previous 70% that you've analyzed that you've trained the model with, right?
Yeah. So what we do is we actually predict on both if you think about it. So when it's training, it's actually predicting on the training set. But then we have a separate step where we do a prediction on the 30%, which is data that it's never seen. Yep.
In a real-time application, you've done the past X number of years of data, and this is the last time that you trained that. Is it an ongoing training that is?
Absolutely. I'm glad you asked that question. So here's the thing, and that's a whole other topic, but it is a part of this conversation. So I'll go ahead and say it. You have to routinely retrain your model because things change over time, right? So the trends that you have in your data today may not be the trends that you have in your data 2 years from now, right? Or the trend that you had in your data 2 years ago may not be the same as the trend in your data 5 years ago. So deciding how you're going to do data selection to train your model is very important. super important. I'm glossing over those details because, I mean, it is important, all right, but I don't want it to detract you from using this as a tool. I want you to be able to take some data, run it through this thing, look to see if there's signal. See, part of it's just experimentation, right? To just see, is there signal in this data? Is there something here? And it would take you literally less than 5 minutes to do that with this. Is to pump some data through it, use all the boilerplate code that's already there, don't change a thing, and see if there's signal in the data. Yeah, you have to have it on a retrain schedule based on trends in your data. And so, yeah, knowing how your data is shifting and moving is important to know when it's time to retrain a model. So doing the analysis of the performance of the model is important. So you can say, hey, I'm going to go ahead, I'm going to do a retrain. We're on a quarterly retrain, for example. Maybe you set up a schedule because you know how your industry moves. And you set up a schedule to do it. You do a model retrain, and then everything just falls apart, right? So then you got to go into your data, and you have to see, all right, what's going on in our data? Is there been an introduction into our data set that has shifted everything? And believe me, we could talk for hours about problems in doing this type of work, where I've had signal in data before and lost it, and it can happen with the introduction of new data. So yeah, retraining models is important. Understanding when to do it is important. But we're not going to get into those details today. Yep. I decided because I've used it as a tool before. Yep. Yeah, so the analysis of the performance of the model is something that's super important. So what you can do is you can load the output of the prediction, which has both the label that you're predicting and what you actually predicted, and look at that in the context of all the features and even all the data in a tool like Tableau, which is not an area of expertise that I have, but there are people that love doing that sort of stuff. And what they will do is that they will dig in and they will see exactly where the model's performing well, not performing well. And then again, it's a cyclical process, right? You're just like with software, you're always trying to improve upon it, make it better, make it more this, make it more that. Models, you're always trying to improve for one reason or another, whether or not it's not performing as well in this particular scenario. And then maybe you don't even worry about that because maybe that's not the most important scenario for you to focus on. But maybe what you could do instead is, instead of changing the model, maybe change the code around the model, right? There are tons of different ways for you to deal with that sort of stuff. But I'm running out of time, I think. So what I want to do real quick is instead of going through the other two models that I had, is I want to show you a quick demo about and talk quickly about model deployment. Because I think there's concern about, all right, I've done all this work, I built this model, all right, how do I productionalize this thing, right? How do I make it real? How do I make it something that I can use in my application right now? So there is an answer to that question. All right, we're going to bounce on over there. Yeah, okay. And I've done all three of these things, and there are probably more ways for you to do it as well. So one way would be to expose your model as an API endpoint, right? So you can put your model behind an API, have people call the API endpoint, give it a JSON payload that are the features of the model, boom, you got your prediction out. That's one way to do it. And I will demo that in just a second. Another way to do it is to use something like Aws Lambda, which is amazing. I've done this for production models where you deploy Aws Lambda. They have Aws Lambda, they have API Gateway, and they have something called S3 buckets. S3 buckets holds your model, so you push your model and all its dependencies up to the S3 bucket. API Gateway is where you specify what the API to the model is, and then you bind it to Aws Lambda. and AWS Lambda is just a function as a service, and then models are perfect for that. Absolutely perfect. The one downside to it that I have found is if you do not have consistent calls to it, you have the cold start problem. And then so for applications that have timeouts, these short timeouts and things like that, AWS Lambda can be a problem, but there's a solution to that problem as well. We could talk about it offline if you want. Because if you have somebody hitting your model once every, one time they're hitting it at 1 o'clock and then there's no activity for 3 hours and then they hit it again really, really hard. If you have sporadic usage, then it could be an issue. And then AWS Lambda has space constraints around it. I think you can only put 250 megs worth of code in AWS Lambda. The problem with AWS, it's not a problem, but it's a reality. Every dependency that your model has at prediction time has to be on AWS Lambda. So if you trained your model with sklearn, guess what? sklearn's got to be on AWS Lambda. If you took dependencies on any libraries, guess what? Those have to be on AWS Lambda. Every dependency that you take on in your model training has to be on AWS Lambda. So you have to be careful, because I've had this happen. I got beyond the 250 megs, and then I couldn't use AWS Lambda. So what I did instead is I went to Elastic Beanstalk. And Elastic Beanstalk is super cool, because what you can do on Elastic Beanstalk is you can still expose your model as an API endpoint on Elastic Beanstalk, and they handle all the scaling for you. You don't have to worry about it. It's pretty cool stuff. And you don't have the space constraints that you have on Lambda. All right, demo time. All right, so super, super simple stuff. Anybody familiar with Postman? All right, great. Oh, where'd it go? Come on. Work with me, dude. You're not working with me. All right, let's see if I can do this a different way. Nope. All right, so this will be fun. All right, so what we have is here's a JSON payload, and then up top you can see I'm hitting this localhost web server that I'm running. It's really simple. It's a Flask web server. If you've worked in Python, you know about Flask. It's not scalable. Who cares? We're just demonstrating something. And then here what you have is you have a payload that the model expects. Now, the thing that I did is in all three of our models that I have, they all have exactly the same features. 3 different models, all the same features. So what I'm going to do is I'm just going to say send and hope that it gives me a result, which is going to give me the same result it gave last time. So let me change that to, golly, I cannot see that. So what we did is we gave it the features, and then it gave us the run pass of run. So that was the thing that we just looked at, right? So we had 2 possible outcomes, run or pass. We gave it the features, and then immediately it came back and it gave us the result. You saw how fast it was. It's super fast. And unfortunately, I'm blind and can't see. So let's see how this works. All right, I'm going to do the binary. Class. So I just created 3 API endpoints for the 3 results. I don't even know if I typed that right. Binary classification. Yeah, that's not how I wrote it. So let's take that out. 1, 2, 3, 4, 5. Thank you for your patience. Shazam. All right, so all we did is we just created an API endpoint, which is just a simple Flask web server. If you want to see the code, it's stupid simple. It's like 5 lines of code or whatever. And we were able to call our model, predict, return a result immediately, right? And so that is the message that I want to get across is predictive models can be used as a tool to solve traditional business problems in companies today. I think it can be used to replace rules-based systems. I feel it can be used to replace even computation if you're within range of your Y target. So please explore. In a week or so, I'll get this up on GitHub. My tag on GitHub is Passionate Programmers Guild. I'll write it down for you if you want it. I'll post it on LinkedIn so that you can pull this stuff down, play with it, put it through your data set, send me feedback. If you have any questions, email me. I'll give you my email address. I want to promote this because there's too few people working in this industry in this town, and I want to change that. So help me change it.